So, final speaker of the first session is Xin Zhang from South China University of Technology, and the title of the talk is Gesture Recognition Using Signature Features.
Okay, good morning everyone. My name is Xin Zhang. I'm from the South China University of Technology. It's a great honor to present our work today. It's a gesture recognition using the signature features, and we are the first group using pass signature on the hand gesture recognition, and we have published 2 relevant papers. So I will, this is the joint work with my master student, and also collaborate with Professor Jing, Professor Lai, and Dr. Ni Hao and Yang. So here are the content I will talk about today. First, I will review what is a hand gesture and what are the popular applications of hand-based interaction. And also I will talk about the research challenges. And after that, I will talk about 2 frameworks we have proposed. One is trajectory-based hand gesture recognition, the other is skeleton-based hand gesture recognition, and then I will conclude my talk. Okay, so firstly, hand gesture is usually regarded as a hand or arm or upper body movement. It's not the whole body movement, but mostly related with the hands. So the hand gesture is a very efficient way to communicate between people when you guys talk, like right now I'm using my hands. And so it's also a very natural way to interact between human and a computer. And so the hand-based interaction is considered the next generation of the human-computer interaction. So it is very important, and because it's a wide applications. The first application I want to talk about is sign language. Sign language here is not only involving with the hand gesture recognition, but also involved with the language model. So this is a very important research topic for the hand gesture recognition, because once your computer can automatically recognize your sign language, and you can directly communicate with the computer. The other application is the immersive environment, actually the virtual reality. This is a test version. It's not really, if you guys have played with Oculus or any virtual reality camera, right now you cannot reach this kind of control. What you are using right now is this kind of control tools. You need to hold something, because the accuracy cannot support this kind of elegant control. But this is something we are working on. We hope one day when you are wearing this camera, and then your hand will be there controlling the virtual environment. So this is a very important application for the hand gesture or hand-based interaction. The other is the semi-immersive. We call that augmented reality, mostly presented by Microsoft HoloLens. This is quite different from the previous slide, because what your hands are doing here is not only interact with the virtual thing, but you are controlling the virtual thing interact with the real object. So the key research or key challenge here is not only to understand your hand movement, but also the 3D reconstruction. But what we are focusing here is accurate hand tracking and hand joint estimation. And also, this is in the gesture recognition field, this is the most popular applicable application. It's a control system in the car. This actually, if you have a BMW i7, I think you will have this kind of experience. Like you can use your hand when you're driving one hand, and then you can use the other hand to answer the phone call, switch the sound, and change the volume. This is the system. It is in the market, and so far as I know, a lot of car companies are focused on develop and put this system in their car. They think this is a safe way when people are driving. You don't have to focus on your screen and touching or anything. You just wave your hand or use your voice. So this is another application. Furthermore, you can wear some armband or data glove to control some mechanic devices. So all above are the possible applications based on hand gesture and hand applications. And so to summarize, the gesture-based research focus on all 4 topics here. First is sign language, and hand pose estimation, which mainly to estimate all 22 joints of the hand. And then for the hand gesture recognition, they have a dynamic hand gesture, which means you gesture or something you want to convey based on the moving hand motion. The other is static hand gesture, means you are posing something like this way, and there we call that static hand gesture. All those are research topics in our group, but today I will focus on the dynamic hand gesture, because static hand gesture mostly can be regarded as image recognition, and the dynamic hand gesture, the hand trajectory and the fingertip trajectory can be regarded as a path, and we can use path signature to further extract the features. So my talk focus on here, dynamic hand gesture. Okay, here are some research challenges. I list the 5 major challenges, but actually there are more. First one is similarity. Vision-based hand gesture recognition, we base on RGB or RGBD, so we mainly based on colors. And the finger and palm and our face body, in most cases, are similar colors. And also fingers have similar structures, so they pose a lot of challenges. The second one is occlusion. When you do a gesture like folding the hands, when you see that, definitely some part is occluded by the frontal objects. And so hand may also holding some objects. There's occlusion, self-occlusion, and other object occlusions. The third one is individual variations. Everyone's hands are different. Some are bigger, some are smaller, and some have long fingers. So that's called, we refer that to individual variation. The fourth one is environment. It's typically for the vision-based research because it is so sensitive to the light, to the surrounding environments, and to a lot of things that might change your color or change the environment. The fourth one is computational cost, because if you really want to do something applicable, you must make sure it is fast with reasonable accuracy, and also your hardware cost cannot be very high. So this is a very typical problem for real-world applications. After review the challenges, I will talk 3 typical related research. These one are very typical framework for the vision-based dynamic hand gesture before deep learning. Okay, before deep learning appeared, people follow this flow chart, but they will use different way to do the hand detection, hand tracking, and the features. And I'll focus on the features because what kind of feature we're using will depend on how representative ability of your feature sets. So there is a lot of feature people have developed, have used for the vision-based classification, but all these features are usually manually designed, and it is sensitive to light environment. It is a common issue for the vision-based research, and not robust enough for color similarity, and a limited representation for the structure problem. So all these features have their limitations. That's why we have path signature coming. But with deep learning, people also propose some very interesting framework for the hand gesture recognition. For example, this is the problem. These people, this guy, can you see what he's cooking? He's cooking, and we want to understand what he is doing. So we need to understand hand movement. Okay. What people are proposed here, they use CNN, convolutional neural network, as a feature representation. They extract feature based on CNN, and then they use several STM as a sequential representation. The LSTM actually, in short or in summarize, is like they want to characterize the sequential event temporally. They want to characterize the temporal dependency within this temporal sequences, and then after that you have a predictor, which is a classifier. This is a very typical model of deep learning based long event or long sequence understanding. They reach very nice result, but the major limitation is this model is very complex, and they usually require hundreds of hours training, and the model size is very large for a small hardware to implement. So this is the biggest challenge for this kind of framework. And the second one is they propose some simple work. This work, although the flowchart is for human, but they can easily apply for the hand gesture. And before us, before our work, this work reached the best results. And they just fully use the temporal spatial information and model them by the RN recurrent neural network Dr. Ni just presented. So they use that to model the temporal information beneath that. Similar thing, the model training is a big problem. Okay, so our research focuses on the recognizing various hand gestures using RGB or RGBD sequences without wearable devices. So I want to say a little bit about without wearable devices, because right now the most accurate hand recognition is you wear data glove or you wear an armband. But that's not something we are trying to do. We try to develop something natural for human to interact. You want to wear something before you interact. So RGB or RGBD sequence are the best choices we have. And also, essentially, this is a key part actually. When you characterize the hand movement as a set of trajectory, no matter finger trajectory or hand move trajectory, and then all those trajectories can be represented as a path, temporal path. And then these paths can be further characterized by path signature features. So this is our fundamental idea here. Okay, I will introduce two frameworks we propose, but the first one is the hand trajectory-based hand recognition. So in this framework, we treat or we only consider the gesture which use whole hand movement, which means we're just waving or doing something, treat hand as a whole, but we don't separate hand and finger-based activity. So in this case, the hand trajectory will be considered as a path. So this is a hand trajectory, like we are waving, and then the trajectory further can be extracted like this, and this is our trajectory. And we do the data augmentation by rotation, translation, scaling, and random dropping. And after we do the augmentation, we can use path theory to extract the allowed path signature features. And then these features will further feed into a classifier, which is a typical CNN-based classifier. This is our general framework. I will explain one by one. Okay, firstly is the signature feature definition. After we detect the hand and extract the movement in the 2D space, that will be a set of discrete points, right? And then whole movement will be represented as a set of discrete points. And then we can define a window-based path on here. This is A. It is a path corresponding to this part. And then we use log path theory to compute the log path signature based on this short path A. And then we reorganize them as image-wise. So that is the case, like if we have path A here, we have 8 figures. This is trunk 4. So we have 8 figures, and every dimensional path signature will be put in the same position into these images. And the following will do the same thing. And then based on that, one hand trajectory will be converted into 8 images representing different level of path signature. And these are all the feature set will be fed into the further image-based classification. So I guess when we first use this one, the question is like, why don't you treat them as a vector, but treat them as an image? Because as you can see, let me show the figure here. These are all the all the 10 different hand gestures we are using, and all their corresponding LPS features. Okay, and you can see they have their spatial pattern if we preserve them in the image format. So we want to represent them in a path signature and also preserve their spatial patterns. So that's why we convert them into image-wise representation like this. And these are the features of every gesture. And then these features are packed as a whole feature representation set, and we'll go them into the convolution and the fully connection layer, and this is the output for the final classification label. this is the general classifier. So let me review this one. We have a hand extracted result as a trajectory, and then we do the augmentation, and this is the path signature feature extraction, represent them into a different level of path signatures, and then we will use CNN for the final classification. So this is a data set that we use for testing. This is from the University of Sheffield, and I think it's mobile. Okay. I point out 4 these gestures because they are most confusing gestures. You can see the lightning situation is very bad, and the motion is very similar, especially these two. One is rotating, one is this one. So this is very confusing gestures, and our results, we compare 2 frameworks. One is we only use RGB, that means we don't use depth information, only the color information. The other is we use both RGB and depth information. When we only use RGB, we reach the best result, even better than the RNN framework. And for the depths, we are the second best because this one have optical flow, which is a motion information extracted from the data. But I think for the fair comparison, we are comparable or the best among the all the current algorithm. This is the first framework we propose, and this is the second or latest framework, the work we propose, and it's just being accepted by AAI 2019. This framework is one step further, because previously we only take hand as a whole part, but now we want to treat them as a hand, arm, and the finger separately. And then we can represent more complex hand gestures. So what we can do here is right now we have, the input is not just a hand as trajectory, but input as a skeleton. That means we have a finger, a hand, and arm all as our trajectory part. And then we propose this temporal variation TTM, temporal variation module, which means we not only consider the path signature can very powerfully characterize the single sequence temporal variation, but when consider different sequences, like different people performing different gestures, they have inter-sequence differences. So we use this TTM to characterize their temporal variation, and then we use multiple path signatures, and then we use a multi-path framework to finally convert them together. This is a general idea. I will explain one by one. So we have 3 contributions, or with 3 new things we propose in this work. One is attention of hand, because we have all those skeleton joints, which joint to be used and what kind of path to be defined. So since we're only focused on hand, so we only concern about hand joints on the hand. That's the first thing. And then what are the relationship? Temporal relationship is based on time. How about spatial relationship? So we define the joints, which is several joints together, so as a set. And then we propose this one temporal transformer module to elevate the temporal variation of a key frame. The last one is how to fuse different type of signature features efficiently. These are the features or the we are using. We use raw coordinate, and we use temporal, spatial, temporal path signature, which is inspired by Dr. Yang's work, and he will talk about this afternoon. And basically, we have the temporal path signature based on the temporal trajectory variation. And we define on the spatial path signature, which is a pair of joints, which means in a certain frame, I want to study the joint-wise relationship. I've defined that as a path, and then I will define signature of signature to characterize spatial temporal signature. So these are the whole framework. So input still the image sequences, and then we extract the skeleton. These can be implemented easily by RGB sensor information or open pose. And after we extract the joints, we have AOH, attention on hands, means we only focus on joints on hands and the joints pairs between hands, within hands, and hands and body. And we define those as a path signature pairs, and we extract the spatial path signature based on based on joint pairs, and we extract the temporal signature based on the joints along the time, and also we convert them together to extract a temporal spatial path signature here. And this is temporal spatial path signature. Okay, so we have raw coordinate, we have temporal path signature, spatial, and temporal spatial path signature. All four kind of path signature will all be used as our feature to represent the hand trajectory. And then this is a dyadic method. Dyadic method we use here, this is not proposed by us, but I think it's a very interesting idea. It's like, if you have path signature, you want to characterize the temporal information globally and locally. So we use the dyadic method to compute the path signature. So globally, you will use this one as a path to compute path signature, and locally, you will use several separated paths to feed in to calculate path signature. And in this way, we can characterize the temporal variation globally and locally together. So this is a temporal transformation module. The fundamental idea is very straightforward. It's like the path signature we compute is only by sequence, but actually different people do different gesture. They will have a different tempo. For example, if I wave hands, I can wave hand fast, or I can wait and wave hand slowly. So in these two different cases, the key frames are different. The key frames are different among sequences, but this kind of variation has not been characterized by the final classifier, because our final classifier is very simple, fully connected layer. We want to keep the model as simple as possible for the real-world application. So in that case, this kind of temporal variation cannot be characterized by this kind of simple classifier. So as you can see, we extracted all the neurons along the time, and these are lighter, means they have strong weights, means they have response, they are expecting the key frame. And these are the dark area, means those neurons are less attention, meaning if you have key frame in this region, you have less ability to be recognized. So this kind of temporal variation between sequences will give us problem. So we are thinking probably we can propose something to learn this kind of temporal variation. Actually, people have done something like LSTM or RNN. They are proposed a structured way to learn this temporal variation. But we don't want to use this kind of complex model. We want to keep the model simple. So we're thinking probably we can use some data-driven way. And actually, some people have already used this kind of data-driven way. What they have do is they do the data augmentation, like they shifted their sequence randomly to increase the training set to try to cover all the possibilities. But in our experiment, we find out this is not a good way, because when you have more data, the model are confusing and they don't know what exactly you want them to learn, even though your goal is to learn the temp shifting. So we are propose this kind of learning-based TTM model, which is like based on the data, based on your input, I will learn this data, delta. And this delta will tell you how your sequence will shift to make sure your key frame matches the final classification active neuron. So, and this delta is not predefined. It is sequence by sequence learning based. And this module can be implemented or incorporated into any different networks. So based on this one, this TTM model, and so this TTM model will run on every raw coordinate and joint pairs before they put into the feature extraction and path signature feature extractor. So I will align sample temporally to alleviate the temporal variation. And then the last contribution we have is we have a multi-stream, because our features are different. We have raw coordinate, temporal path signature, spatial path signature, spatial temporal path signature, and originally we put them all together. We truncate them all together, but because they're different. If you just put them together, they will it won't reach the best result. So we propose a multi-stream results. It's like I will separate them. Raw coordinate, spatial, temporal, they are separate. They will have their own separate fully connect layers, and the final weights are also learning based. So these are all the things we have proposed, and we have tested our method on 3 major data sets. And of course, we need to do some pre-processing like augmentation and centric normalization and the range normalization. This is a pre-processing we have done. And this is the data set we have tested. Well, this is the data set based on 20 Italian gestures, Italian sign language. It is interesting, this data set is collected by some Chinese researcher, and they do some 20 Italian gesture, which we don't know, we don't understand, and some gestures are really challenge for us. And they have provide RGB, depth, mask, and skeleton, and they have 1,000 training, 1,000 validation, 1,000 testing. So we mainly based on these data sets. So first, the ablation study, this one. So we want to test the truncated level and with different path signatures. And as you can see, with more and more path signature, the result reach the better. And when truncated level goes larger, the result also gets better. But the thing is, when you have a larger truncated level, you will have a very large dimensional feature sets. So we want to trade off. So we have a different truncated level for different path signature. And the other one is we investigate with a TTM, some time variation we have proposed. We have tried mainly 2 things. This is one means we don't have multi-pass. Okay, just a single network without TTM, and a single network with the TTM temporal enhancement. This is something I talk about the data-driven way. It's like you don't learn that shifting. You just increase your data set by shifting around and make your data set larger. But actually this one doesn't improve, but in the contrary, decrease, because more data set will confuse your model and leads to other problems. So what we have is like we have the TTM with the temporal enhancement, we have the best result. That means the delta, the time shifting part should be learned, that'll be more powerful based on that. And this is the multi-pass accuracy. If you have a multi-pass, you will reach the best result. And also, we compare our algorithm with other people on this Learning 2013. And we reached the best result with our proposed method. And also, you can see this is the multiple ads comparison, means we are faster. We have extremely less computation requirement because our classification model is very simple. So, and our result is the best among others. And this is a comparison of Learning 2016 and MSRC 12. Well, this one we reached the best result. And this one I want to explain a little bit because people on this data set are all use RGBD and optical flow. We are the only 2 methods use only skeleton because skeleton give you less information. But if you want to use RGBD, that will introduce more computational load. So we are within our territory, we're still the best in the comparison. So these are the challenge. I don't know whether to play. These are the challenge gestures. This coming and type OK and adopt. You see, only just small hand movement. So these 4 are very similar in terms of classification. And also I have another type. It's hand moving around the head. So even you see the skeleton, you probably cannot directly see the difference. So those are the challenges considered about the noise in the skeleton estimation. So a little advertisement, we have collected 3 large data sets. One is the ego gesture, like you can interact with people. And this is the largest one so far as we know. It's egocentric, that means you're wearing a camera on your glasses. And this is a gesture. We have multiple gestures on the egocentric view. And also we have collected new data set using the multi-modality and static and the dynamic gesture. We will release this one soon because we just finished collecting. So conclusion is hand gesture is a very important and interesting topic for the hand-computer interaction. And by considering the temporal variation and designing a specific structure, we can further improve the results using the pass signature. So the future work probably, I think, we can propose some learning-based framework that incorporate with the signature features and how to define a minimal pass. It's a very interesting topic for the pass signature. Thank you very much.
Questions?
Have you any thoughts on how to incorporate the cultural interpretation? For example, if an Irishman made a particular gesture, it might mean something quite different to an Italian making the same gesture.
Yeah, that's a very interesting question. As long as there's a data set, we can incorporate the differences. But the challenge we are facing right now is we don't have a lot of data set. The CHA Learn, that's the biggest one, and they stopped collecting. So all people on hand gesture field, they are testing on all 20 Italian gestures. And we're kind of expert in Italian gestures on that.
Is your training and testing across different subjects, or is it the same subject can be in training and testing? How's the evaluation done, please?
Yeah, thank you. That's a very good question. And in their data set, they have separated that well. So it's actually cross-subject. That means training subject will not be in the testing subjects, not in the validation subject. So they are separate subjects. But if you want to mix them, you can mix them by themselves. Yeah.
And anything, any tool or code or something published, any package published?
Their data set is available online.
Not the data, like the actual tool you've developed?
Our program?
Yeah.
I think the first one we have put on the GitHub. The second one we just published. We will publish that, but not very soon. Yeah.
Last question.
Question to both you and Terry. How much work has been done on the pipelining of the inference? What is the impact of the way it's actually implemented?
How to implement the inference, or
Yes.
what
sort of hardware do you do it on, and what's the impact of parallelizing that the way that you're doing it?
Okay, so we're just extracting the hand gesture as a pass, as a signature, and how to define the pass. After we define the pass, we will use pass signature theory to extract the features, and then we use feature further feed on the classifier. So if you want to say that, will be just several general steps. So you will say if we use pass signature but with different inference, a different classifier, I think that will reach different results. So that's why classifier need to be specifically designed based on your problem. Another question.
Only to say maybe that there is a package out there for doing the transformation from path to signature.
You have, yeah.
Yeah.
Terry
Not
has.
terribly fast.
Terry has.
I was
Can
guessing
certainly
more
be
of
improved.
the kind of
But
the
there is actually a
hardware.
Python package that anybody can do.
Okay.
Pip install and it's done.
Yeah, Terry provided us on the pass signature support.
Okay, so I think thank you very much for all three speakers.